Hey everybody, thanks for coming. So we invited Matt about this time last year to give a talk, and it's been a year. Since that time, he has started his own group, and he has already put it 2 high-profile publications on the online. And so it's very great for us to invite him back to give another talk about new data in his new paper. So for those of you who were not here this time last year, Matt got his PhD from University of Arizona. He did one of the first experiment using STM to study the Moiré superlattice between graphene aligned with the boron nitride substrate. And then he did his postdoc at Correlated group at Columbia. And one of 2 of his most high-profile publications during that time is to first integrate high-pressure measurement to study how the response of a graphene boron nitride superlattice. And then he used the same technique to study the superconductivity in magic angle twisted bilayer graphene. So he demonstrated that both the magic angle and superconductivity in twisted bilayer graphene can be controlled using hydrostatic pressure. And so moving on, I think that he's going to talk about twisting 2 different graphene layers together. And instead of superconductivity, he's going to talk about very novel and intriguing ferromagnetism that comes out of this Moiré superlattice. So Matt.
So yeah, I won't get to the ferromagnetism until the end, but I think there's other exciting stuff to talk about. So hopefully everyone can stand to see me for a 2nd year in a row. So I really appreciate the invitation and the ability to speak again. I'm trying to share my screen. Can you see it, Leah?
Yes.
You can?
Yeah.
Okay. So this is the first virtual seminar that I'm giving, which means that it's the first time that I haven't had to frantically rearrange my slides on the flight over. So we'll see if that's a good or a bad thing. And please interrupt me either over the chat or just by voice. If you have any questions, I'm happy to treat this as if I were there in person. So I'm going to talk about some of the results that we've had over the past year or so since I moved to the University of Washington and started my group in the departments of physics and material science. And the talk will broadly focus on tuning or tunable correlated and topological states in twisted graphene multilayers. So here's the basic outline of my talk. I think everyone by now is probably pretty familiar with the concept of van der Waals materials and heterostructures, and even some of the newer stuff that's happened in the past couple of years in terms of realizing correlations in these heterostructures. So I'll just give a very brief overview of this. And then I'll talk a little bit to set the stage about twisted bilayer graphene, and then really focus on some of the more recent work we've done in twisted double bilayer graphene and twisted monolayer-bilayer graphene. And then if I have time left, I'll finish with the discussion. And you can see here that there's a little bit of weird twisted graphene math. So I'll hope to convince you that in twisted bilayer graphene, we can say that 1 layer plus 1 layer equals 2. In twisted double bilayer graphene, 2 plus 2 equals 4. But in twisted monolayer-bilayer graphene, 1 plus 2 gets a little bit weird. All right. Probably not many people need to hear this, but we know now how to isolate a really wide variety of materials down to atomic monolayers using a simple Scotch tape exfoliation technique. And now in the 2D limit, these materials basically have any property that one might want to study in condensed matter physics in bulk counterparts. So we've known about metals, semiconductors, and insulators for quite a while. And there's emerging materials now that in the 2D limit are superconductors, ferromagnets, and topological insulators. So this field is really booming in terms of the number of materials that we have accessible. But really the power of the field comes in the ability to take these isolated atomically thin materials and stack them together into a heterostructure. So this can be done by a dry transfer procedure that was developed at Columbia about a decade ago, where you simply pick the layers of these crystals up one by one and assemble them into a heterostructure that you desire. So here's just a simple heterostructure of graphene encapsulated between 2 flakes of boron nitride. you take a cross-sectional TEM image, you can see the individual boron nitride and graphene layers. And of course, this is not something that you'd ever find in nature, but it's something that you can easily assemble in the lab. And really the phase space here is enormously large. You can basically make whatever heterostructure of these 2D materials that you desire. Of course, there's other experimental tuning knobs that you have accessible upon stacking different van der Waals materials. So if I just take two hexagonal lattices like graphene and boron nitride and overlay them, the lattice mismatch means that I get this emergent geometric interference pattern called a Moiré pattern. And then if I change the twist angle between these two crystals, I can change the period or the wavelength of this Moiré pattern, which effectively acts like a superlattice for the graphene. And as Leo mentioned, some of the STM work I did about 8 years ago now, helped to highlight that these Moiré patterns are really quite important in modifying the material's properties. So here's an STM image of graphene and boron nitride, and you can see a small hexagonal lattice highlighted in white, arising due to hexagonally bonded carbon atoms in the graphene lattice. And then on top of that, there's a larger hexagonal superstructure, which is this Moiré interference pattern between the two crystals. And we can make different samples with different twist angles, and this Moiré pattern goes from large to small as we tune the twist angle from small to large. And this follows a simple geometric dispersion, so basically everything works as the geometry should dictate it should. Now, if I stack two metals on top of one another, like two layers of graphene, for instance, then their band structures can be highly modified. They can hybridize strongly and can change substantially as a consequence of this Moiré pattern. So if I look at the band structure of monolayer graphene, we know that at low energy at the K and K prime values, we have this linear dispersion. And then at higher energy, there's a Van Hoff singularity, and then the mass of the band inverts. For a twisted bilayer graphene at small twist angle, the band structure looks very much similar to monolayer graphene, but now the energy scales are substantially smaller. So whereas in monolayer graphene, we're considering bands on the scale of electron volts, now the low energy bands of twisted bilayer graphene are on the scale of tens of milli-electron volts. And in some very simple hand-waving way, you can think that this Moiré pattern is effectively acting like a much larger unit cell for the graphene. And so we recalculate the band structure and everything looks roughly similar, but now all of the energy scales are smaller because this lattice constant is much larger. Now, it's helpful to think about what's happening to the bands of twisted bilayer graphene a little bit less schematically. So we can imagine that when we have two rotated bilayer graphene sheets, in momentum space, we have these two Dirac cones, which are slightly offset due to the twist angle. And now if we turn on an interlayer coupling term between these two graphene layers, these crossing points at the center of the Moiré-Brillouin zone become avoided crossings and they gap out. And so these low energy bands end up getting flattened towards zero energy. Now there's a special symmetry of twisted bilayer graphene called C2 symmetry, which is basically 180-degree rotation symmetry. And this is equivalent to exchanging the valleys within a single layer of the monolayer graphene. And because those values are identical, the symmetry is respected. And the symmetry is actually responsible for protecting Dirac crossings at zero energy in the band structure of twisted bilayer graphene. So we essentially have a tuning knob, a single tuning knob from the twist angle to be able to control how flat these bands are by considering this kind of geometric ratio between their offset and momentum space and how strong the hybridization is that induces a gap at full filling of these Moiré subbands. And in addition to tuning with twist angle, some of my prior work showed that we can also tune this gap directly with pressure by modifying this interlayer Moiré coupling strength directly. But I talked about that last time, so I'll skip it for now. And okay, so we can calculate then for a fixed interlayer coupling strength what the bandwidth of twisted bilayer graphene is as a function of twist angle. And we see that it actually tends to vanish around this so-called magic angle of about 1.1 degrees. And when this happens, the kinetic energy of the electrons in the system are quenched, and the mutual Coulomb repulsion between electrons, which is mediated on this Moiré length scale, becomes a dominant energy scale in the problem. And in this case, we would expect that at low temperature, we might find ground states driven by correlations, Whereas in the more usual regime where the kinetic energy dominates over the Coulomb energy, we would anticipate that the ground states would be uncorrelated. And indeed, work from Pablo Herrera's group at MIT in 2018 really sparked kind of a massive new field, or a new subfield of van der Waals engineering, in which they realized that two sheets of twisted bilayer graphene, or two monolayer graphene sheets twisted to 1.1 degrees, basically gives you access to more or less any state that we know about in bulk materials and condensed matter physics. So we can tune between metals, band insulators, superconductors, correlated insulating states. With additional conditions, we can realize ferromagnetism and quantum anomalous Hall effect, really all within a single materials platform, and all tunable just by changing the charge carrier density. So this is, really quite an exciting field to pursue in this regard. But twisted bilayer graphene is not alone, and it turns out that there's actually more generic ways that we can realize flat electronic dispersions in these van der Waals heterostructures. So if we consider instead just twisting semiconductors, which have more conventional parabolic dispersions, the symmetries of these crystals dictate that not only do we get an energy gap due to low energy block band formation at some finite positive and negative energies, but we're also able to tune the band gap at the neutrality point with a perpendicular electric field. And so now we have control over the width of these bands, not just with twist angle, but also at a fixed twist angle by applying a perpendicular electric field. And this is relevant in a number of different twisted van der Waals heterostructures, like twisted double bilayer graphene and similar, which I'll talk about today, and even more disparate systems like twisted WSE2. We can be more general than this even. We can just take a standard semiconductor that already has a somewhat large effective mass and impose some sort of superlattice potential on it, be it from a Moiré pattern or probably even otherwise. And this also gives us a similar path towards realizing flat electronic bands. So this Moiré pattern will create these low energy block bands. We have an energy gap, which can often be tunable at the neutrality point. And this again gives us some sort of general path towards realizing some flat dispersion with correlated states. So this is relevant in systems like rhombohedrally stacked or ADC trilayer graphene aligned with boron nitride to get a Moiré pattern, and also WSE2 heterostructures. So I can create this new kind of taxonomy of flat band van der Waals twistronic systems, which have correlated or topological ground states at low temperature. And to my knowledge, there are what I would consider 7 distinct systems now that have been discovered in just the past 2 years that can do this. On the left here, we have our graphene variants, so twisted bilayer graphene, double bilayer graphene, bilayer monolayer. If we align these things to boron nitride, they really form fundamentally distinct electronic states. So I'm going to consider this as a different system entirely. We can have trilayer graphene aligned with BN and even variants of twisting different transition metal dichalcogenides. And I have no doubt that there will likely be more than just these 7, which are discovered in the coming months and years. Okay, so with that, I want to now focus on what happens in particular towards the left side of this chart in these twisted graphene heterostructures. So to set the stage, I'm going to talk briefly about twisted bilayer graphene and use this kind of as a way to just get the nomenclature and expectation for how these systems behave for when I go on to the more recent results. So what happens if we take 2 sheets of graphene and twist them and then measure electrical transport? Well, if the twist angle is large, then it basically looks like 2 sheets of monolayer graphene measured in parallel. So for above 3 degrees, the conductance of the sheet is low at the neutrality point, and then it grows as we dope the system with more electrons or more holes. But if we make the twist angle smaller now and the Moiré pattern grows bigger, then something distinct happens as we start to dope with more electrons or more holes. The conductance eventually saturates and then drops to identically 0 before recovering to some finite value again. And this is roughly particle hole symmetric. All right, so somewhat remarkably, we can take 2 metallic sheets of graphene, stack them and twist them at just the right twist angle, and out of it we get tunable insulating states. And these insulating states, as I alluded to earlier, are actually understood very well at a single particle level. So the hybridization of these two metallic graphene bands leads to these low energy Moiré subbands, and then they're isolated from the higher energy dispersive bands by some energy gap. And so this energy gap is responsible for the insulating behavior. And again, this is single particle level. And by convention, I'll call this these plus or minus n sub s or n sub superlattice, basically the number of electrons or holes necessary to fill these low energy flat bands. Now, of course, the discovery that sparked this field came from the MIT group. I'll summarize with data from my own more recent devices, where if you make a sample at the magic angle of about 1.1 degrees, in addition to the insulating states that you see at full filling, you also see insulating states emerging at commensurate quarter fillings of the bands. And by now we've seen them at basically all of the quarter fillings. So these correlated insulating states are not expected in a single particle model. They're coming at partial filling of a band. They should be metals. Instead, they are really driven by something analogous to either a mod insulator or a quantum Hall ferromagnet, or likely something in between. But that still remains an open question. Now, if we go slightly away from the commensurate quarter fillings and measure the resistance as a function of temperature, we see that it actually quickly drops to our noise floor, basically immeasurably small at low temperature. And this is indicative of the emergence of superconductivity in the system. So within a single material, we can make a phase diagram of the system by measuring the resistance as a function of charge carrier doping, which we can do electrostatically with gate voltages. And so at some densities, we see metallic behavior, the dark blue. At others, we see pockets of superconductivity, the cyan. And at others, we see correlated insulating states, the red and yellow. And we can freely tune between these just by changing the voltage knob. Okay, so with that, I'm going to move on now to a question of what happens if I add more graphene layers to the problem. And so somewhat counterintuitively, the simpler one to start with is what happens if I have a bilayer and a bilayer. So I'll talk about this, and then I'll go on to removing one of those layers and twisting a bilayer and a monolayer. All right, so as I mentioned at the beginning, twisting two bilayers gives us an extra tuning knob because now this system doesn't have this C2 rotation symmetry. So we don't have protected Dirac crossings at the neutrality point, and we can tune the bands as a consequence by modifying the gaps at the neutrality point with an electric field. And the system has been, characterized initially by 4 different groups about a year ago now, who all posted their papers, I think, on 4 consecutive days on the archive. And they all found some rough variant of the same phenomenological behavior, where when they measure the resistance in the color scale as a function of the doping and as a function of the electric field on the vertical axis, they see tunable single particle band gaps at the neutrality point and at full filling of the bands. And then they see the emergence of these correlated insulating states, most strongly at half filling of the conduction band, and then also more weakly under certain conditions at quarter and 3/4 filling, surrounded by this kind of odd halo-like feature marked by increased resistivity. A number of groups noticed that if you slightly detune from the half-filling correlated insulating state and measure the device resistance as a function of temperature in this halo region, you see something that's roughly linear in T down to some low temperature of around 6 Kelvin or so, and then it abruptly drops towards 0. Maybe it hits exactly 0, maybe it doesn't, but it's something at least suggestive of a superconducting transition. So, beyond the initial characterizations of these structures remain open questions as to essentially what is the nature of these correlated insulating states in this surrounding halo feature, and what is the nature of these abrupt downturns, and is this actually indicative of superconductivity in the system or not? Okay, so some of the work that we've been doing, kind of my group in collaboration with Xiaodong Zhu's group at the University of Washington over the past 6 months or so, is to look at transport in these twisted heterostructures of bilayer graphene and bilayer graphene, encapsulated in boron nitride with top and bottom graphite gates. These graphite gates allow us to change the charge carrier density as basically the sum of the 2 gate voltages, and the electric field as the difference of the 2 gate voltages. Now, we can calculate what we expect these bands to do as a function of the electric field or the interlayer potential U. And it turns out that it's somewhat complicated. So a lot of things change at once when we change the electric field. But here are the salient features. Without an electric field, we have somewhat flat conduction and valence Moiré mini bands separated by an energy gap from the more dispersive remote bands. And these bands actually overlap. So the system is a semi-metal without an electric field. When we start applying an electric field, we actually open an energy gap at the charge neutral point, so that isolates the valence and the conduction bands. But that comes at the expense of these gaps to the remote bands. So those will eventually close. And then as we apply an electric field, we can also tune the flatness of the conduction and valence bands. And that turns out to happen oppositely. So the conduction band gets flatter with the electric field and the valence band gets more dispersive. And again, this feature is not present in twisted bilayer graphene. It's really a consequence of the fact that we've broken this C2 rotation symmetry in the twisted double bilayer graphene lattice. So lowering the symmetry basically gives us more experimental knobs to play with. Now we can calculate the density of states from this band structure as a function of the doping, or what I'll call the filling factor, roughly analogous to the language of some sort of degenerate quantum Hall system, where each one of these bands is fourfold degenerate for 2 spin and 2 valley degrees of freedom. So full filling now is what I'll call nu equals 4. That's when the chemical potential is has completely filled the conduction or valence bands. And when we calculate the density of states, of course, it's consistent with these band structure calculations. We see the density of states vanishes at high displacement fields at the neutrality point. It vanishes at full filling and then actually becomes semi-metal again at high displacement field. And then we also see these regions of high density of states corresponding to Van Hoff singularities and band edges within these flat valence and conduction bands. And these disperse with electric field in certain characteristic ways. Okay, so the first thing that we want to do is measure transport at slightly elevated temperature of 30 Kelvin, so that we suppress any possible correlation effects and just understand what we know from a single particle level. And when we do this, we find that actually this single particle model works pretty well. So, the main features that we see are insulating states emerging at the charge neutral point, 0 carrier density at finite displacement field, insulating states at full filling, nu equals plus and minus 4, and then this cross-like feature, which resembles this cross-like movement of the Van Hoff singularities within the flat valence band. Okay, so the general things that we understand about this system are pretty well understood from the single particle model. So now we want to cool the system down to 20 millikelvin and see what of that survives and what new might emerge. Okay, so the salient features here are actually quite similar to what we see at high temperature, including these gaps in neutrality, the gaps at full filling, and now a sharper version of this cross-like feature. But in addition, we see new features which are not explained by the single particle model. So those are these insulating states now that emerge strongly at half filling of the conduction band, more weakly at quarter and 3/4 filling, and then also this halo-like region marked by a weak increase in the device resistivity. And this is a pretty sharp boundary between the inside of the halo and the outside at low temperature. Okay, and because we can't understand these from the single particle model, we don't anticipate insulating states at partial band filling. We attribute them to consequences of correlations within the flat conduction band. We can get a bit better of a handle on what's going on by also considering the Hall resistivity. What I'm showing you is a Hall coefficient, and really you just need to concern yourself with whether the color is red, white, or blue. So red tells you that you're measuring electrons, blue tells you that you're measuring holes, white tells you that the system is roughly balanced between the two. So we see sign changes as we anticipate across the neutrality point and across full filling of each of the bands. We see an additional sign change at partial filling of the conduction and valence band, which is necessary because the band is closed. So every electron that we initially fill into the system eventually has to be balanced out by some hole. But then we see that these halo-like features correspond to interesting regions where the sign of the Hall coefficient is actually opposite from what we would anticipate from a single particle model and what we see at displacement fields that are outside this halo region. And we see little replicas of these halos at quarter and 3/4 filling. So the main question right now is, what is this halo region really telling us? And to get a basic idea, we can consider what is the consequence of actually opening a gap at half filling of the band. The consequence is that we have to break some symmetry in the system. the band is initially fourfold degenerate and spans filling factors 0 to 4. And it has 2 spin and 2 Valley degrees of freedom. And if we're to see an insulating state at half filling of this band, that means that we have to break spontaneously one of these symmetries and open a gap. So if we imagine that the chemical potential is just slightly under half filling, that means that we're just below a Van Hoff singularity in the parent fourfold degenerate band. So we would be measuring electrons. But if the band is spontaneously symmetry broken, now we could be in a condition where we're measuring holes, even though the system in a single particle model wanted to be electrons. So that's kind of a basic understanding of why the sign would flip. And to get a better handle on this, I want to measure this now as a function of temperature and see how this symmetry breaking evolves. So I'm going to show you the resistance at fixed carrier density as I sweep the displacement field for 8 different values of carrier density. And so those are these maps. Let's start with the one at half filling. What we see is basically this arch-like feature beneath which we have diverging resistivity. It's red, it's very high. And this one corresponds to the case where we're precisely at half filling, and the boundaries of these arch at low temperature are basically mapping out the boundaries of this correlated insulating state. I didn't mention, but this correlated insulating state seems to need that both the conduction, both the neutrality point and full filling are insulating so that the band is isolated. Now, what happens if I detune from half filling? In this case, I still see the arch-like feature, but it gets smaller. This arch-like feature gets smaller and eventually disappears as I detune too far away from half filling. And also, the arch-like feature is metallic. It's no longer insulating. So I can take a few cuts to show you the temperature dependence to illustrate this. So if I take a cut precisely at half filling here, you see a kind of standard metal insulator transition owing to the formation of this correlated insulating state below about 13 Kelvin. If I take cuts at filling factors that are slightly detuned from half filling, the system is metallic, but it's a very odd metal. So at high temperature, it has this kind of canonical linear and T behavior that's standard of multilayer graphene. But then below some temperature, roughly around the onset of insulating behavior, it has this abrupt downturn in resistivity and saturates to some lower value. And this onset temperature of this abrupt downturn depends on where I take this cut. So if I take it precisely at the center of this arch, then the temperature is high. If I take it at the edge of this arch, which means the edge of the halo, then the temperature is low. And again, this contrasts what we see outside of these halo regions, where we don't think the system is strongly correlated. And in that case, the temperature dependence looks a lot more conventional of graphene, where we have linear and T decrease of the device resistivity as we cool, and then at low temperature it saturates, owing to the freezing out of phonon scattering. All right, so what I want to argue then is basically that these abrupt downturns are actually signatures of this spontaneous symmetry breaking. So in the same way that this insulating state of precisely half filling is a consequence of spontaneously forming a gap in these bands, these metallic states at slight detuning of this half filling still have some remnant symmetry breaking owing to their proximity to half filling. And as a consequence, they still exhibit some unusual transport. Now, you know, these sharp downturns also are qualitatively similar to what you might expect in a superconducting transition. So one thing that we want to do first to rule that out is ask, well, you know, is there characteristic nonlinearity when we measure transport as a function of a DC current bias? And it turns out that the answer is yes, these things are nonlinear, but we think that they are not actually nonlinear in a way that's indicative of superconductivity for 2 reasons. One is that the nonlinearity persists not just within regions inside this halo where we see these abrupt downturns, but also in regions outside this halo region completely. So for example, this burgundy and this yellow curve are not within these evidently correlated regions, and yet they still exhibit you know, not unsubstantial nonlinear transport. Whereas in contrast, if we go far, you know, to a very metallic region, we do see linear transport. Now, again, this doesn't really look like superconductivity in the sense that we don't have sharp quasi-particle peaks, and we don't have saturation to a fixed normal state resistivity at high applied DC current bias. Instead, I think this is a consequence of Joule heating. And the reason that we believe that is just a consequence of plotting this as a function of the dissipated power in the system. So basically the voltage times the current. And what we see is that the more nonlinear the transport is, the more power they're actually dissipating. And this is somewhat of a unique system. The base temperature resistivity can be quite high, on the order of kiloohms, so the heating can be quite substantial. And also the temperature dependence can be very large at low temperature. So for example, this green curve, as we heat, the resistivity grows quickly. So there's somewhat of a positive feedback mechanism in the sense that once we start heating it, the resistivity gets larger and then it's easier to heat it. And so the nonlinearity grows and grows. So we think that despite kind of superficial similarity to superconductivity, we're pretty sure that this is actually a heating effect. And we also never see that this device resistivity actually saturates to zero resistance. So instead, our understanding is that these sharp downturns are really a consequence of spontaneous symmetry breaking of these bands as a consequence of developing correlations as we cool the system. So we can illustrate that a bit better by taking kind of zoom-in maps of the device resistivity around this halo-like region. And as we warm the system, we see that this halo kind of collapses into this broadly resistive stripe at high temperature. This is a bit confused by thermal activation to remote bands, so we can look at this in the Hall coefficient instead. And here we get a bit of a sharper measure of this halo-like region, which is basically traced down in white. And what we see is that this halo-like region collapses towards half filling as we raise the temperature of the system and eventually disappears. And if I were to just track the Hall resistivity at a fixed point slightly away from half filling, you can see that we're actually able to change the sign of it simply by cooling the system down. So again, we think that this means that this region in blue corresponds to what we would expect the sign of the Hall coefficient to be from a single particle model. And this region in green is the opposite of that. So we think the green indicates some sort of spontaneous symmetry broken region. We can investigate this in a bit more detail by looking at this map at 20 millikelvin and measuring the Hall density at fixed displacement field as a function of filling factor for different displacement fields. So the Hall density is just basically 1 over the Hall resistance. And what we find is that outside this halo region, it basically behaves as we anticipate from single particle expectation. The Hall density grows as we dope, and then abruptly changes sign as we cross the Van Hoff singularity, and then shrinks back to 0. So this blue coloring region indicates that we think that there is standard fourfold degeneracy of these bands. But within these green colored regions, as we start pushing into this halo, you can see that the sign of the Hall density abruptly inverts from what it should be from a single particle model. And then as we push into these replica halos at 1/4 and 3/4 filling, we get yet another inversion. So those seem to indicate that a single degeneracy is lifted upon the formation of each of these correlated insulating states. So the green regions correspond to twofold degeneracy, and the orange region corresponds to no remaining degeneracy. And so I can just construct these things into a phase diagram, which should mimic what this is doing, where I'm just coloring based on whether the sign of the Hall coefficient is what we expect or opposite of what we expect. And so the blue regions correspond to regions outside the halo, where the parent band is evidently intact and fourfold degenerate. And then this halo is a footprint of how far we can detune in filling factor and displacement field from the optimal conditions and still realize some symmetry breaking of these bands. So basically these bands gap and the degeneracy is reduced by 2. And then not shown when we go to 1/4 and 3/4 filling, we get yet another symmetry breaking of this twofold symmetric band. And now this orange region has no remaining degeneracies. All right, and so I want to return now to the question of why we have these abrupt drops in resistivity. And one important feature of this system is that from in-plane measurements, in-plane magnetic field measurements of the energy gap at half filling, we think that these bands are spin-polarized. So this energy gap represents a spin-polarized excitation. And so if we're probing just a single one of these bands, it's valley unpolarized, but it should be spin-polarized. And so there's some sort of magnetic ordering that we anticipate in these metallic regions within this halo that are neighboring this correlated insulating state at half filling. And if I just go to other systems that have been measured in the past with either ferromagnetic or anti-ferromagnetic ordering, it turns out that there's actually some qualitative similarity in the way that transport looks below the Curie or Néel ordering temperatures. So for example, in manganese silicon, there's a ferromagnetic transition that's tunable with pressure, but you see this linear in T temperature dependence, and then this abrupt drop below the Curie temperature, and then the resistance is much smaller at base temperature. Similarly, in barium, iron, and arsenide, there's an antiferromagnetic transition below a Néel ordering temperature of about 140 Kelvin, and again, you also see this abrupt drop in resistivity. And these are thought to arise because there is less scattering in magnetically ordered states. So, we don't have a good probe of whether this is a precise mechanism. It may also be related to different photon scattering modes within these symmetry broken bands, but at least there's some qualitative similarities between these. All right, and the last thing that I want to show you in this system is the ability to tune the phase diagram with twist angle. So this is kind of a data dump, but what I want you to look at are these phase diagrams that we can construct from the Hall coefficient. As we tune the twist angle, the region of symmetry breaking grows until it's about roughly maximal at 1.3 degrees. You can also see that there's only correlated insulating states around 1.3 degrees. For lower or larger twist angles, we don't see a correlated insulating state, but we do still see this symmetry broken region. So that suggests that even when we're not at non-optimal twist angle, and even when the bands don't fully gap, you can still be sensitive to the fact that you have some sort of spontaneous symmetry breaking in the system as you cool it down. All right, so if there's no questions to this point, I'm gonna move on to a new system that we've studied that really hasn't been investigated before. And basically removing one of these graphene layers now and looking at a twisted monolayer-bilayer graphene heterostructure. All right, so the name of the game is pretty similar. We make these encapsulated structures now of a bilayer graphene and a monolayer graphene with a twist angle of around 1 degree. And again, we can calculate the band structure. We think that we understand a lot of things from the single particle level in the same way that we did in twisted double bilayer graphene. But now there's a new ingredient. I have to show you both calculations for positive and negative electric field. The system has reduced symmetry still from the twisted double bilayer graphene, which was symmetric with electric field. Now we're breaking an additional symmetry, which is this mirror symmetry in plane. And this MY mirror symmetry basically exchanges the top and bottom components of this heterostructure, or more formally, it exchanges the valleys within the Moiré-Brillouin zone. One edge of this valley, the K valley, is a monolayer-like dispersion, and the other is a bilayer-like dispersion. So when we switch these, we get something different. So this symmetry is now also broken, whereas it is not natively in twisted double bilayer graphene, which would be the same by switching the bilayer graphene on the top and bottom. So reducing the symmetry again gives us yet more experimental knobs we can use to tune the correlated states in the system. We can tune it with both electric field and the sign of the electric field. So to illustrate this and to try to build some expectation for what we might expect, we can calculate the local density of states. So basically how the charge arranges itself on each of the 3 graphene layers in the heterostructure. So the bottom 2 are the bilayer, the top one is the monolayer. And these are very different now as a function of the sign of the electric field. So for electric field negative, which by convention we define as pointing from the bilayer towards the monolayer, the local density of states strongly localizes on the 2 graphene layers at the rotated interface and arranges itself on this triangular lattice of ABB stack sites, where basically the lattices exactly sit on top of one another. And then this outer layer of the bilayer graphene has very, very low local density of states. So it's basically a small amount of charge in that layer. Whereas in contrast, if we flip the electric field and have it point towards the bilayer graphene, the arrangement of the local density of states is still similar. It's still peaked on these ABB sites. But now we've pushed a lot of the charge towards this outer layer of this bilayer graphene. So these two systems look very different depending on the sign of the electric field. And in fact, what I want to convince you of is that there's kind of a simple analogy we can make to either twisted bilayer graphene or twisted double bilayer graphene, depending on the sign of the electric field. So if we do this calculation for twisted bilayer graphene, it looks very much like it happens with the D negative side of twisted monolayer-bilayer graphene, but it's missing this extra layer with only a small amount of charge. Nevertheless, this layer may act as somewhat of a screening perturbation on the system. So, we can draw some rough analogy between these two. And in the same way, when we flip the sign of the electric field, the local density of states looks very similar to twisted double bilayer graphene, except now it's missing an additional layer that's only weakly charged. So from this, we might want to think that 1 + 2 is either equal to 2 or 4, but not 3. So we can do, without further ado, some experiments to see whether this actually holds water. And so what we're going to do is measure a sample with a twist angle of about 1.08 degrees at 300 millikelvin. And I'm going to show you a similar thing to what I showed you for the twisted double bilayer. Resistivity is a function of carrier density and electric field. So a lot of the salient features of twisted double bilayer graphene are reproduced here. We have these tunable gaps at the neutrality point. We have gaps at full filling. But now what is distinctly different is that I have to show you both sides of the displacement field, and they're not symmetric. Whereas in twisted double bilayer graphene, they were to within our experimental resolution. So, again, a lot of this can be understood at a single particle level. If we just calculate the density of states, we see that there's a lot of similar features in terms of kind of Van Hoek singularities that move throughout the valence band and insulating states at neutrality and full filling. But I won't go into details about precisely how well these match. I want to instead focus on these correlated states, which are different between positive and negative sign of the displacement field. All right, and again, we can play the same game where we measure the Hall resistivity. And again, we have regions around these correlated insulating states where the Hall resistivity either flips sign broadly over this extended halo region, or takes short excursions to the wrong sign around these 3 correlated states at quarter, half, and 3/4 filling on the negative displacement field side. So that's suggestive that correlations are somehow creating some sort of symmetry broken renormalization of these bands. All right, so to look at this in more detail, let me remind you now, just to orient you, the positive displacement field corresponds to the regime in which we think that we should be measuring something like twisted double bilayer graphene, and the negative displacement field side looks like something that should be resembling twisted bilayer graphene. So I want to go through these one by one and see how well these analogies actually hold up. So I'm going to start with just a broad overview of a comparison of each one of these to their analog states in twisted double bilayer or twisted bilayer graphene. So in the positive displacement field sign, we see this correlated insulating state surrounded by this extended halo-like region. And indeed, that looks quite a bit similar to what we see in twisted double bilayer graphene. And in contrast, on the negative displacement field side, we see these 3 roughly equivalent states at all quarter fillings of the bands. And that's reminiscent of what's happening in twisted bilayer graphene, where we have insulating states at each of the quarter fillings of the bands. Okay, so I'm going to start with the positive displacement field side and show you the temperature dependence for, I believe, 0.5 volts per nanometer, which is cutting through this correlated insulating state. And we see that indeed there's an insulating state that develops precisely at half filling as we cool the system down. And then if we look at slight detuning of this correlated insulating state, we see the resistivity has these abrupt drops, indicative of this spontaneous symmetry breaking of the bands. Again, we can also measure the Hall density, and we see that it has extended regions where the Hall coefficient has the wrong sign. And this basically has a one-to-one mapping to twisted double bilayer graphene, where we have these abrupt drops in resistivity neighboring these correlated insulating states. We have these extended regions of the wrong sign of the Hall coefficient. And measurements in an in-plane field also suggest that these are spin-polarized states, the same as they were in twisted double bilayer graphene, where the device resistivity grows larger as we apply an in-plane magnetic field because the spin gap is getting bigger. Okay, so that one is somewhat trivial. The more interesting one is what happens when we look at the D negative side, which should be roughly analogous in our cartoon picture to twisted bilayer graphene. In this case now, we don't actually have correlated insulating states. We have what I'll call correlated metallic states, where we have these resistive bumps at quarter filling, but the resistivity shrinks for all of these states as we lower the temperature. And in fact, some of them even completely disappear. So at quarter filling, we see this state at high temperature, but it's gone at low temperature. It turns out that we've seen similar things in twisted bilayer graphene as long as we go to samples that are not exactly at the magic angle, or in samples that have electrostatic screening, such that we can marginalize the effective correlations. And I should point out that Leo has done really a fantastic experiment in this regard. And so what we see in this case is, okay, well, there's a correlated insulating state here, but the ones at quarter and three-quarter filling are also these similar correlated metallic states, where we see these clear bumps at high temperature and they get smaller, or at least they're not insulating as we lower the system's temperature. And the thing that's different about twisted bilayer graphene and twisted monolayer-bilayer is that in this system, we have the ability to further tune these with electric field. So whereas these states are not tunable with electric field in twisted bilayer, we can turn them on and off at different displacement fields in twisted monolayer-bilayer graphene. Now, there's an interesting property of these states that emerges when we apply a magnetic field, and it turns out that these are quite unusual, at least in terms of the types of states that we've seen previously in these twisted van der Waals heterostructures. So the first thing that we can do is apply an in-plane magnetic field. So this is along the 2D sheet. And the in-plane magnetic field should couple to the spin Zeeman because spin doesn't care about the direction of the field, but it should not couple to the orbital Zeeman, or at least not strongly, because it's roughly a 2D sheet. So there's not a strong orbital component out of plane, or in plane, sorry. And when we measure the device resistivity with an in-plane field, we see that really not much happens. So that's suggestive that we don't have strong Zeeman effect of these metallic states. When we apply perpendicular field, something interesting happens. At low field, there's also not much going on, but then abruptly correlated insulating states emerge in what seems like almost a first order phase transition at half filling, at three-quarters filling, around 2.5 or 3 Tesla, and then also an incipient correlated insulating state around quarter filling, although it's never fully developed. At the same time, we see quantum oscillations emerging, starting at high field, but projecting to either half or three-quarters filling, which is suggestive that we're forming new Fermi surfaces as we apply a perpendicular magnetic field. And the perpendicular field should couple strongly to both the spin and the orbital Zeeman terms. Now, the curiosity here is that if these states at zero field were spin polarized, then we would expect the energy gaps to grow with magnetic field in either direction, since either direction of the field would couple to the Zeeman term and grow the spin gap. And in contrast, if these were spin unpolarized states, then we would expect that they should diminish with magnetic field in either dimension, since we would be closing this spin gap by applying larger fields. But neither of these is what happens. We see a state that emerges above some critical field in a perpendicular field configuration, but not in a parallel field configuration. So what we think instead is that these are actually field-assisted, orbitally driven correlated insulating states. And these emerge only above some finite B perpendicular, which is coupling strongly to the orbital degree of freedom, whereas B parallel does not. So we can get a bit more detail about these states by measuring their field dependence as a function of temperature. So for B parallel, I'm only going to show you base temperature since nothing much happens. It's basically flat. But for B perpendicular, we see this very abrupt change from nearly flat magnetoresistance to very, very strongly diverging magnetoresistance in high field. We can define some, we can realize that this is really seemingly a first order phase transition between a metallic phase at low magnetic field, which has weird but approximately metallic temperature dependence, where the resistivity shrinks as we lower the temperature. And in contrast, at high field, say at 3.5 Tesla, we see a more canonical metal insulator transition as we cool the system down. So this behaves like a metal below the critical field, and this behaves like an insulator as a function of temperature above the critical field. So we can characterize this a bit by basically fitting some sort of critical field, which we're just going to define as the crossover point between linear fits to the low field to high field magnetoresistance. And so these start points are what we want to call some sort of critical field, where we expect something like a first order phase transition between a metallic and an insulating state. And we can make a phase diagram here, and what we see is basically that the critical field grows weakly with temperature as we start to warm the system from base temperature, and then starts to grow quickly at high temperature. And below this line, we have a metallic state, and above this line, we have an insulating state, as defined by how they respond to temperature. Now, these types of phase diagrams have actually been observed before in a number of different correlated systems. So for example, in Beschkart salts, under pressure, a similar phase diagram was observed between a metallic and a field-assisted insulating state. And this was thought to be driven by a spin density wave. And in mercury cadmium telluride quantum wells with low density, Wigner crystal formation was thought to drive some sort of phase boundary between a correlated fluid and an insulating electron solid. And we don't know what the ground state polarization of this insulating state is, so we don't actually quite understand how to describe the exact nature of this state. But at least qualitatively, this seems to be consistent with other field-assisted, orbitally driven insulators that have been measured previously. And so we can assemble this sort of cartoon of what the local density of states roughly looks like, inferred from this behavior. So basically, I'm showing you now basically an average over all three layers. This is not a calculation, it's just a cartoon schematic, where the local density of states is localized around these ABB stack sites, but not very strongly at low magnetic field. And essentially that may be because we have an extra layer of weakly charged monolayer graphene in this configuration that could be serving to screen interactions in the active layers at the twisted interface. Now, when we apply a perpendicular magnetic field, we have an orbital effect which confines the local density of states more tightly around these ABB stacked regions. And effectively, that can boost the effective strength of correlations and lead to some insulating ground state above a critical magnetic field. And the cool thing in these systems is that we have quite a bit of flexibility to tune these. So, we can modify these states by applying an electric field, and at a fixed temperature, we can also create a phase diagram where we tune this crossover point between the metal and insulating ground states as a function of the electric field. Okay, so one thing that I haven't considered yet is that these bands actually have non-trivial Chern indices. And in principle, these non-trivial Chern numbers can lead to some sort of anomalous Hall effect. So there's been a number of calculations now for twisted monolayer-bilayer graphene that indicates that indeed these bands have non-trivial Chern number, and these can be tuned with electric field and also with twist angle. So this, in principle, is an interesting platform to search for the quantum anomalous Hall effect. Now, the ingredients for realizing a quantum anomalous Hall effect is that you have non-zero Chern bands, so that's non-trivial, that's trivially satisfied in this system, but also that you have some sort of spontaneous magnetic ordering, and that you can actually realize a gap at partial band filling to polarize into just a single spin or valley sector, such that you don't average out the Chern number to zero when you fill all four bands simultaneously. And this has been done before in a number of different Moiré van der Waals heterostructures. So here's a cartoon from Andrea Young's work in aligned twisted bilayer graphene with boron nitride at the magic angle. And they're able to observe a quantum anomalous Hall effect at 3/4 filling of the conduction band. And basically the picture is that you have 8 bands in twisted bilayer graphene, each with Chern index plus or minus 1. And there's a degeneracy of spin and valley. So you have to somehow polarize into just a single one of these bands. And in that case, you would be able to measure within a gap of a Chern band with non-zero Chern index. So those would satisfy all the conditions for a quantum anomalous Hall effect. And indeed, this has been realized. And what's interesting about this quantum anomalous Hall effect is that it's completely orbitally driven. So normally, quantum anomalous Hall effect requires some sort of explicit time reversal symmetry breaking. For example, in some sort of magnetically doped topological insulator. In this case, there's no explicit time reversal symmetry breaking. We're just measuring graphene, it's just carbon, and so the spin-orbit coupling is extremely weak, and there's no explicit magnetic dopants. The orbital degree of freedom is effectively playing the role of something that will spontaneously break time reversal symmetry. And instead of some sort of condensation into a spin-polarized state, there's a condensation into a valley polarized state where all of the electrons want to arrange themselves in one corner of the Brillouin zone. And so this is what's responsible for, this is what's thought to be responsible for this novel type of ferromagnetism. in these Moiré van der Waals heterostructures. So just as a bit of historical overview from things over the past few months, in samples of magic angle twisted bilayer graphene further aligned with boron nitride, there was a fully quantized quantum anomalous Hall effect that was realized with Chern number of 1. In rhombohedral or ABC stacked trilayer graphene, all aligned with boron nitride, there is a still developing but nearly quantized quantum anomalous Hall effect with Chern number of 2. So in fact, these systems are not only quantum anomalous Hall states, but they also have different and perhaps even tunable Chern numbers. The annoyance here is that this requires careful control of the twist angle and or stacking configuration of the multilayer graphene. And further, you have to externally rotationally align with the boron nitride. So these samples are remarkably difficult to make, and there's really only been a couple of each one of these that have ever been successfully fabricated. So really what we would like is if there was somehow some way to do this intrinsically without having to rely on kind of external alignment with extra crystals. So following the motivation that these twisted monolayer-bilayer systems may intrinsically satisfy this property, we looked at devices with other twist angles. And in a device that we recently measured at UW at about 0.9 degree twist angle, we see a somewhat similar phase diagram to the one that I just discussed. Since I'm running low on time, I won't go into all the details, but the different thing is that on the twisted double bilayer graphene analogous side, we now have an additional correlated state at 1/4 filling of the band, which we did not have in the prior device. And if we measure the Hall coefficient, we see that it's actually very large, over 15 kiloohm, in the region around this state at 1/4 filling of the band, and basically 0 elsewhere. So that suggested that there's some sort of spontaneous magnetic ordering in the system. And indeed, if we park the gate precisely at this point and sweep the magnetic field up and down, we see this very obvious hysteresis loop in rho YX, and also some weak hysteresis in rho XX, which is a hallmark of ferromagnetic ordering. Now, a few things to note here. Rho XX is not precisely 0, as one would expect for a true quantum anomalous Hall phase, and rho YX is not exactly quantized. So evidently, there's some leakiness in the bulk, or the gap is not fully developed. But the Hall angle here is above 10, so it is suggestive that this state in a cleaner device or a device at lower temperature would eventually become a quantum anomalous Hall or Chern insulator. The resistivity is above 12 kiloohm. So the naive interpretation is that this would be a Chern 1 system, although we don't have really direct confirmation of that. And also the temperature to which this ferromagnetism survives is remarkably high. It's a few Kelvin, in contrast to other quantum anomalous Hall systems, which are typically, you need to go to millikelvin temperatures to stabilize. Okay, and I should note that this was also done in Andrea Young's group in samples with different twist angles yet, so about 1.25 degrees. And there they saw quantum anomalous Hall at both 1/4 and 3/4 filling, both with near quantization with Chern number of 2. Whereas our results weakly suggest that at this twist angle of 0.9 degrees, the Chern number is 1. So there's more that needs to be done, but this motivates that, in fact, we not only can realize intrinsic quantum anomalous Hall in these samples without external alignment to other crystals, but also the Chern number might be tunable with twist angle or perhaps even pressure. Okay, so one quite curious effect that we see in this sample arises when we sweep the doping back and forth across this quarter-fold state. So we do this with a small magnetic field of a few millitesla. It doesn't matter which direction we sweep. The sign of the magnetization is set by the sign of the magnetic field. But then somewhat bizarrely, when we do this very, very close to 0 field, we can actually switch the magnetic order depending on which way we sweep the doping. So if we sweep from large doping, we get the positive magnetization state. And if we sweep from small doping, we get the negative magnetization state, all in the absence of magnetic field. We can do the same thing for displacement field, but it doesn't switch in the same way. So this is really quite a curious phenomenon. I'm running short on time, so I'm not going to go through all the details, but you can ask me afterwards or believe me when I say that this does not seem to depend on initialization conditions. So for example, the history of which way we swept the magnetic field to get to 0 doesn't determine whether it chooses a positive or negative state. it really seems to be determined just by the direction of the doping that we sweep from. Okay, so what might explain this unusual phenomenon? Well, doping-induced switching was actually theoretically predicted a few months ago by Alan McDonald's group at UT Austin, and was experimentally realized in Andre Young's experiment at Santa Barbara. But this is a somewhat different effect in that that theory in the experiment relied on some finite magnetic field to set the sign of the magnetization. In fact, it shouldn't work at zero magnetic field. Whereas in contrast, what we find is actually only works around zero magnetic field. Even a few millitesla suppresses the effect. So this really should violate some sort of intrinsic symmetry of the system. And there's no explicit time reversal symmetry breaking. So there's no reason why it should necessarily choose to be up or down deterministically. And so that's really quite a curious phenomenon. And whether this actually turns out to be something that's generic across different samples, or something related to disorder in these samples or disorder in this sample in general remains to be seen. But we think that we've taken care of kind of measuring all of the confounding variables, and this at least seems to be a robust effect in this sample. And so one possible hint may be that if we subtract off the anomalous Hall component to just get the conventional Hall effect sign, what we find is that the Hall effect changes from electron-like to hole-like across order filling. And the chirality of the edge mode is the same for both of these cases. For when we sweep down from positive doping, we're sweeping from electrons with a positive Hall coefficient, and it chooses a positive magnetization. And when we sweep up from low carrier density, we're sweeping electrons, which have the opposite sign, and get the opposite sign of the magnetization. So if you work out the sign of this actually favors, I think, one chirality of the edge mode. So maybe that some sort of inhomogeneity in the edges of the sample is responsible for this switching. But nevertheless, this is exciting if it can be reproduced reliably, because there's, realizing doping-induced switching of magnetic ordering is something that's highly desirable in the spintronics community. Okay, so I have very little time left, so let me just say a few things very, very briefly. One question from all this is, what are the ingredients that are actually necessary for superconductivity? It seems to be robust in twisted bilayer graphene, but we think that in twisted double bilayer graphene, a similar effect is actually not indicative of superconductivity, but from spontaneous symmetry breaking. And there's other systems like ABC trilayer graphene and twisted WSD2 that exhibit similar phenomenology, but I think are more consistent with twisted double bilayer graphene and twisted bilayer graphene. So there's open questions still about which of these systems are actually superconducting and how carefully you have to interpret transport measurements as a function of temperature for identifying a superconductor. So one thing that I can say is that superconductivity in twisted van der Waals heterostructures may require some special symmetries. So for example, twisted bilayer graphene is the lone of these systems that has a C2 rotation symmetry. And there have been theoretical predictions that link superconductivity to this symmetry. So that will be an interesting question going forward. All right, so in conclusion, I've primarily shown you transport in two different twisted graphene multilayer systems. In twisted double bilayer graphene, we have electric field tunable correlated insulating states, and then signatures of spontaneous symmetry breaking in the neighboring metallic states. And in twisted monolayer-bilayer graphene, we have a system that resembles both twisted bilayer graphene and twisted double bilayer graphene, with some important differences, including the ability to realize a robust anomalous Hall phase in ferromagnetism at quarter filling of the band. Okay, so let me just acknowledge the people who made this work possible. Much of this work, basically all of it, was done in collaboration with Xiaodang Zhu's group, and in particular, a lot of this work was done by his graduate student Minhao He at the University of Washington. And some of the twisted bilayer monolayer work was done in collaboration with Corey Dean's group at Columbia and his graduate student Xiaowen Chen. And then we have some external collaborators, including Yaohui Zhang, who did a lot of the theory for our work. Okay, so with that, I'll wrap up and leave it here, and thank you for your attention.
Thank you, Matt. We might have time to, so Gang has a question.
Nice talk, thank you. So in the double layer twisted system, did you use magnetic field to see whether the superconductivity, to see whether there's magnetoresistance effect to indicate whether it's superconducting, or other effects such as weak localization or emergence of magnetism? Yeah.
We look for all of those things. The long story short is that there's not a strong magnetoresistance as we apply a magnetic field in these states. So I think I can show you.
Both in plane and out of plane?
That's right. I mean, there's nothing that's like a very sharp transition as you would expect for a superconductor. Let's put it that way, for either in plane or out of plane. When we apply an out of plane field of 9 Tesla, you can see that basically the resistance within this halo-like region doesn't change substantially from zero field, but you do stabilize these correlated insulating states more strongly.
Okay, a follow-up question, that is, you use graphite and boron nitride as supporting substrates. And what is the required surface smoothness or roughness of these substrates? Do they have to be extremely flat, atomically flat?
They do, yeah. So the magic of all of this is that you have pristine van der Waals interfaces between these crystals. And in addition to providing a high quality substrate for the graphene, they also will expel contamination and basically congregate it into pockets, which you can eject from the sample during the device fabrication. So these interfaces are atomically precise, and they're also, ultra clean. You don't see signatures of contamination in these cross-sectional TEM images. And without that, the mobility of these devices would be very likely too low to see this physics.
Thank you.
Brad, you have a question?
Yeah, thanks. That was a really nice talk. So you discussed this orbital ferromagnetism, but I was just wondering if there's ever been any discussion of a kind of anti-ferromagnetic ordering of these orbital moments. Is there any indication that that might be possible?
Yeah, that's a great question. I think that that's probably the case in the states at half filling and twisted bilayer graphene, for instance. So when we measure, for instance, these states as a function of either perpendicular or in-plane field, we see that they're suppressed. So that suggested that they're spin unpolarized and therefore likely valley polarized. So there'd be like spin anti-ferromagnet, but valley ferromagnet.
I see.
But those don't have the required net buried curvature to yield an anomalous Hall effect. So
Right.
in terms of just measuring that, it's difficult. It's difficult from a transport perspective to be sensitive to anomalous Hall effect when the buried curvature integrates to 0.
Right. But could they be valley anti-ferromagnet?
I think in principle, yes. So these states in twisted double bilayer graphene, for instance, which we think are spin polarized or spin ferromagnet, would therefore likely be valley anti-ferromagnet.
Huh. Well, that's very interesting.
Yeah.
Thank you.
Thank you.
There's one question.
I have a question.
Yeah, go ahead.
Me?
Yes.
Okay, hold on. Where's me? Okay. Hold on. My question is regarding the IV curves for the superconducting state in the one that looks like a can I see the IV?
Sure. Yeah, let me pull them up. Do you see them there?
Yeah, okay. Here you plotted DVDI. What did the IV curve look like? The raw IV curve look like?
So we actually measure DVDI. So we're making an AC lock-in measurement.
So you actually never change the amplitude of your AC current?
We don't change the amplitude of the AC current. We're using a fixed and small AC current and then applying a DC bias. DC current bias on top of that AC.
Okay. So when you do these AC measurement, well, do DVD or AC, you always you have to worry about there is a background signal, right? Where your zero is, your lock-in, right?
That's right.
And then how do you calibrate that? You just
So I think that we're probably not really dominated by that because the zero DC current resistivity is so very large here.
okay.
And we're talking about like kilo ohms, and we're not trying to measure a few ohms.
Okay. So if I look at this DVDI versus IDC, this is look at the green curve.
Mm-hmm.
Does it change if you apply, say, 100 Gauss or 1,000 Gauss or Tesla?
It changes slightly, but not. It changes quantitatively, but not qualitatively.
Okay, so it's definitely not superconductivity then.
I hesitate to make that claim about what it is in general, but for the samples that we've measured, we have not seen anything that's characteristic of superconductivity in the sense that, so there's a few things that we can judge. One is that we don't see quasi-particle peaks or a saturation to a normal state resistance. Another is that we don't see a sharp change in the resistance above some critical magnetic field. And the last thing is that we don't see Fraunhofer oscillations, which are basically unavoidable in these van der Waals heterostructures owing to disorder. So you end up with like pockets of superconductivity and normal metal states in these samples. And then the critical current will oscillate, and we don't see anything like that. So by those metrics, no. And we also don't see zero resistivity anywhere. And in fact, this halo region has higher resistivity than the metallic states surrounding it. And if we just measure the DVDI in a metallic state, so for example, this light green curve corresponds to this dot, which is kind of squarely in a metallic state, then it is perfectly flat as one would expect for a metal. Mm-hmm. But we're also able to measure nonlinearity in metallic states outside this halo region. So for example, on the Van Hoek singularity where the resistance is high, we also see nonlinearity. And if I just showed you the burgundy and the purple curve, you wouldn't be able to tell me which one is within the halo and which one is outside of it.
Mm-hmm. Mm-hmm.
So let's take one last question. Ling, I think Ling has a question.
Thank you, Professor Yankowitz. I have a question of the sign change of the Hall resistance in the correlated insulating state. So my understanding of the correlated insulating state is that the gap only opens at the Fermi surface. So if that's my understanding is correct, so the gap at the half filling doesn't open when before the Fermi surface reaches that filling factor. So why would there be a whole sign below half filling?
Yeah, so that's a fantastic question, and I thank you for raising it. I should be more clear about this. So indeed, we expect the largest gap to be when the chemical potential is precisely at half filling, but this band is rather flat, and Coulomb interactions are large. So the Coulomb interactions, we think, I mean, we don't know the exact numbers of the bandwidth in the Coulomb energy scale, but we think the Coulomb energy scale is similar to or even larger than the bandwidth. So even when the chemical potential is detuned from half filling, Coulomb interactions are still large and can still drive some sort of spontaneously broken symmetries. And so the gap very likely doesn't close, once you slightly detune from half filling. It probably gets smaller, but we don't have a spectroscopic probe of that. But the basic idea is that even if the gap isn't open, even if you detune too far and you start closing the gap, you can still get some sort of symmetry breaking, right? The bands don't necessarily have to be fully gapped to have some sort of signatures of symmetry breaking. So the halo is basically a footprint of how far away you can move the chemical potential before you're simply too far away from half filling to continue spontaneously modifying these bands.
And then I have another question. So I noticed that this doesn't happen in twist bilayer graphene.
Right. So that's also a fantastic question. Twisted bilayer graphene has, I don't have the data here, I should. Twisted bilayer graphene has a distinct behavior where basically the Hall density resets to 0 and then starts growing again at every quarter filling.
Yes.
I think that actually indicates that the system is even more strongly correlated than twisted double bilayer graphene. And in that picture, there's work from Shahalalani's group and also Ali Yazdani's, where they do spectroscopic probes. And what they find is this cascade of symmetry breakings, where effectively you can think of having these 4 degenerate Dirac cones. And when you start filling from neutrality, you start putting charge into all 4 equally. But then once you get to quarter filling, one of them fills all the way and it sucks the charge out of the other 3. And then your chemical potential is effectively back at the neutrality point for those first 3 Dirac cones. The 4th one is filled. So the Hall density in that case doesn't actually change sign. It just resets to 0. And I think that's a consequence of correlations being even stronger, because then you're spontaneously filling an entire band rather than just creating a small gap between them.
Okay, thank you.
Okay, so thank you, Matt. If you have more questions, feel free to stay behind. And yeah, it's a great talk. Thanks, Matt.
Thanks, Leo. Thanks, everyone.